So welcome to this Meow seminar with Stephan Gocht, who's going to talk about his PhD project on certifying algorithms using pseudo-Boolean reasoning. So without further ado, Stephan, the floor is yours.
So hello, everybody. I want to talk about certifying algorithms, what this is, what you can use it for, how we think it should be done, namely with pseudo-Boolean reasoning, and give an overview over my work of the last 5 years, essentially. So let's get started right away. Kind of the central question is, do you trust your computer? Right? Like you have some kind of problem, you give it to your computer or your favorite solver, maybe your calculator, because you want to add some numbers, and then it spits out an answer. Say it says 41. But like, do we know that this is the right answer, right? Like programmers often make off by one box. So it could be that there's actually an error in our algorithm or software, right? And then there's still the question, like, do we really trust our algorithms? Especially what is if the answer that is produced by this algorithm is used in some like high stakes decision, maybe like during a combinatorial auction or kidney exchange program. Or today I heard in the radio that I think it was Spain, they have like an algorithm who decides how much police protection a woman needs after domestic violence. And like if this algorithm gives the wrong answer, it could be that the woman is in real risk. Because she should have get police protection, but the algorithm was like, nah, we don't need that. So like, do we trust the algorithm? It's really like an important question, especially the more we use algorithms. And then, well, we can try to make sure that our software doesn't have problems. So for example, we can just make sure that we extensively test our algorithms, that we run a collection of test suites. But then the problem is it really depends on like how good are the tests, how many do we have? And it's likely that we might miss some of the bugs in our code, especially because testing is like only showing the presence of bugs. It's never showing their absence. But then there's also formal verification. So we could try to use some interactive theorem prover to actually formally prove that our tool or algorithm works on all possible inputs. And then if it does, then you know, like whatever input you give it, it will give the right answer. But the problem there is that while this can be done for like increasingly many problems, it's still out of reach for really complex and especially performance critical applications. So then there is kind of a third solution, namely certifying algorithms, what I'm going to talk about in this talk. And the idea here is that we don't only let the algorithm produce an output, but also prove that the answer it gives is correct. And how this looks like, we will see in the talk. Essentially, it's like a sequence of simple steps that are machine verifiable. So how does this look in our small example here with this bug that has infected our algorithm? The algorithm is now producing a certificate, and then we can use an external tool like a verifier that is like taking the certificate and the answer and figures out, no, 41 wasn't the correct answer actually. So it can detect bugs. But also if the algorithm produces the right answer, namely 42, then we can guarantee that this answer is indeed the correct answer by verifying the certificate, the proof that we got from the solver. So why would you want to do this? Well, I mean, when you run your tool or your solver, then, well, you can increase the trust in the solution because now you have another person that's saying, well, that's correct. It's like talking to a colleague, telling him your idea, and then the colleague says like, yeah, right, that makes sense, right? So you have increased trust. But also, like, it's not just that the software could have a failure. It's also that the hardware could produce a failure, so that we can also detect because we have the actual answer that is verified. And then you could also imagine using this after you're done with solving your problem to analyze how the solution was found, maybe to improve the performance of your tool. Or also you could imagine that you store away the proof somewhere, and if later somebody comes and asks you, why did you get this answer? Like, then you can pull out the proof and say, like, this is what we did and why we believe it's the correct thing. And then the person can audit what you have done. And also, like, even before all of that, namely during development, it can be extremely helpful Because let's say we want to do testing still, then usually a problem with tests is that you need to know what the correct solution is. And for some problems, it's like much easier to come up with a problem, but difficult to really make sure you have the correct solution. But when you have a certifying algorithm, you just come up with your test case, you make sure that you certify the answer, and then you know that the answer produced is correct. And also it can help you find bugs, even if the answer is correct, right? It could be that you get the right answer, but you get so using the wrong means, like you did something that only works on this input, but not on other inputs. And maybe you can also help you find where's the first error in your program, right? If you only know after running for an hour that the answer is wrong, then it might be difficult to figure out why. So you can check like, oh, what's the first step that went wrong? Okay, so but what do we need for this? What do we need for having certifying algorithms? So first, like the most important thing is that we should be able to verify it, and it should be like easy to verify. We want the machine to verify it, so it should be like in a very like standardized way that we can write a program that verifies it. And ideally, we want it to be so simple that the proof checker can be formally verified. Like if the proof format is really that simple to verify, then it is very well within reach to like do this formal verification for the proof checker, even though if it's not for the solver. So what we want from the verification side is that we have simple, easy to verify steps or rules. And we will later see what these are in our proof system. And then on the other side, of course, the certificate needs to be created by the solver or algorithm. So it should be easy to implement, like creating the certificate in whatever solver you have. And also like producing the certificate shouldn't take a lot of time, right? You don't want your algorithm to run a lot longer just because you have it explain what it's doing. So from the production side, we want that the rules are very expressive so that they're easy to use and very concise. So there is a bit of tension here also. Like on the one hand, we want the rules to be very simple, to be easy to be verified. On the other hand, we want them to be like expressive to make it easy to output rules. So we will have to do some trade-off here. Right, but still the question is like, how do we do this? I mean, it sounds all amazing, but like how could one possibly do such a thing? Well, it turns out that in SAT solving, there has actually been quite a success story of certifying algorithms. So what is SAT solving? SAT solving is the satisfiability checking of propositional formulas. And there is a SAT competition where like the best solvers compete every year for the prize of the best solver. And it turns out that they, in the SAT competition, it's required to produce proofs. And this has kind of a history because it turns out that some solvers were fast and produced the correct answer on the benchmarks from the competition. But on some other benchmarks, it turned out to produce wrong answers and they kind of were fast by the wrong means. So it's like important to like make sure that it's not only the correct answer, but was only also obtained by this legitimate means and not by taking a shortcut. And then in SAT solving, there has been like a series of proof formats such as RAP, trace check, grid. But like kind of DRAD is nowadays the standard that every SAT solver supports, and that's like used throughout the SAT competition. However, it turns out that it seems, at least to us, that DRAD isn't quite the be all and end all, because already in SAT solving, there are some techniques for which we don't really know how to do DRAD proof logging in an efficient way that it's actually usable. Examples are parity reasoning, where it is known how to do it, but it requires lots of overhead, but also symmetry breaking or symmetric explanation learning. But we don't have to limit ourselves to SAT, right? And if you don't use these techniques, it can mean an exponential loss on performance. So like on some problems, you really want to use these techniques to be efficient. So you also want to be able to verify them. But also we can look beyond SAT because there are like other problems that where it will also be extremely nice to have these kind of certificates that are like somewhat related to SAT. For example, max SAT solving, which is an optimization version of SAT, or constraint programming, where you have like different very powerful constraints which you can use to describe your problem and then solve it automatically. Also mixed integer programming, algebraic reasoning, or what we will see in this talk, pseudo-Boolean satisfiability and also optimization. So for these kind of things, we need to look beyond DRAT, like the standard in a set competition. And it turns out there are actually quite a number of new proof formats being developed over the latest years. Like some examples here are propagation redundancy. There's like a proof format for integer programming that's specifically geared towards the branch and bound algorithm. There's a proof format for algebraic reasoning. Or there's also a version of RAT which kind of can be extended by your own rule, so that you can make it simpler for the solver to output proofs. And then, of course, like we have the pseudo-Boolean proofs that we are going to talk about in this talk. So let's get a bit more into detail, but still stay on high level. So the idea is we want to work on pseudo-Boolean constraints, which are just 0-1 linear inequalities. And we are going to use these to describe the problem that we want to solve. Here are like some examples of pseudo-Boolean constraints. And like a solution is then just an assignment of 0-1 to the variables, such that all of the constraints are satisfying. And this turns out to be an NP-complete problem. So it's like very expressive. You can like express any other NP problem using this. But in general, it's difficult to find a solution. But it's not what we want to do anyway, right? Like we already have a solver and we just want to explain what it's doing. All right, then what's the proof system? So proof system is then a small set of rules that we have to agree on are correct and that are easy to verify. And the idea is that each of these rules is allowed to add a new constraint, and it's using previous added constraints to do so. And the idea is that we guarantee that if there was an optimal solution to our problem before, then after adding these new constraints, there will still be an optimal solution, so that we don't remove optimal solutions, so that we can still get a correct answer. And then a proof is essentially like just like a sequence of these rules, and it will produce a sequence of constraints, say D1 to DL. Again, each of these constraints is derived by one of the rules that we have in our proof system. And also each step can be annotated by additional information that's necessary for efficient verification. And then the idea is that at the end of our proof, we could, for example, derive a constraint that is obviously a contradiction, namely 0 greater equal 1. Like there is no way to assign whatever variables we have to satisfy this constraint because it's always false. And because we have this guarantee that if there was a solution, like there will be a solution in the end also, but there is no solution to 0 greater equal 1. So this must mean that there wasn't a solution to begin this. And thereby we have a proof that the problem doesn't have a solution. Or similarly, if you have an optimization problem, and we want to have a proof of an optimal solution, we can derive a constraint that is like saying, oh, like every solution has to have at least this objective value. And then you know that there can be a better solution. And if you then have a solution that matches this bound, then you know, indeed, you have the optimal solution. And in the rest of the talk, we will like explain these concepts and refine them a bit and say what's going on in detail. All right, so again, in this talk, we're going to use like pseudo-Boolean proofs. We have like a verifier that checks these. And like the amazing thing I think about this approach, also compared to like all the other more recent proof formats, is that it seems to be like really versatile and essentially a multi-purpose proof format. So we can do proof logging for a wide range of problems and algorithms. So first, obviously, we can do 0-1 linear inequalities because that's what it's designed to do. But then also it turns out that you can use it for constraint programming. And like for proof logging of like the algorithms they have in constraint programming, such as the all-different propagation. You can also use it for graph problems, which is a bit surprising because like a pseudo-Boolean formula doesn't know what a graph is. It doesn't know what nodes are, what edges are. It doesn't know anything about graph theory. But it turns out that you can really nicely express a lot of the graph results using like this pseudo-Boolean proof format, and we will also see an example in this presentation where we are going to do maximum matching with it. Then we can also just do anything that you can do with the existing standard for SAT, because our proof format is designed to be a strict generalization of the most dominant proof format DRED. And we are able to do like one of the things that are difficult for DRED, namely parity reasoning and also symmetry and dominance breaking. Sadly, I won't have the time to go into detail how exactly these things work. But you can like look up our papers, and then might also find some of the IIII presentations online maybe. And then also we can use it for translating different encodings. So for example, one way of solving pseudo-Boolean problems that have these pseudo-Boolean constraints is to just take the pseudo-Boolean problem, re-encode it into a CNF problem, and then run a SAT solver. And so far, you could only verify the SAT solver, but with our tool, we can now also verify this translation step. All right, so then let's get started with our running example, which is matching. And the idea of matching is that we have a bipartite graph. So I have one here with me. We have on the left-hand side denotes U, and on the right-hand side denotes V. And the idea is that we want to find a subset of the edges. So the edges are just like connecting the circles here, such that no node is incident to two edges. So for example, if I have like this edge in my matching, then I can't also have this edge because now the node A would have two edges. And what we want is to like show that the matching that we're going to find is optimal. But first we need to express this problem as a pseudo-Boolean problem. So again, we have variables which are 0 or 1. We can also have the negations of variables, which is notated by this bar over the variable. And then a pseudo-Boolean constraint is just linear inequality over literals. So for example, we can say that not the like if x1 and x2 are both set to 0, then this constraint here, this constraint here would be falsified. But if at least of one of these variables is set to 0, then it's true. But if both are set to 1, then this evaluates to false. Or we can also have coefficients over the variables. So essentially what this constraint is saying, either x2 needs to be true, or if x2 is false, then both x1 needs to be true and x3 needs to be false. And then a formula is just a set of constraints. Then we have an objective function, and without loss of generality, we want to minimize this objective function. And then you can also like classify pseudo-Boolean constraints. So for example, a clause is just an at least one constraint, which is also known as a disjunction of constraints. So like either x1 is false or x2 is false, which is the same as saying at least one of them is false. And then we use like this bottom symbol for saying contradiction, which is just a constraint that can possibly be satisfied, like 0 greater equal 1. And the goal is to find an assignment that minimizes the objective function. So if we go to our matching problem, then what we want to do is we want to have variables xij, and this variable should be true or 1 if the edge ij is in the matching. Right? And then the next thing is we want a maximum matching. So we want to have as many of these variables set to true, which is the same as saying we want to set as little as possible to false. And we just sum over all the edges in our graph. And then we need to ensure that no two nodes have a matched edge together, and that there's no node with two matched edges. So we have as a formula, we have the constraints that says like, well, I can't have the edge ij in my matching, and also the edge ik. So one of these two edges may not be in the matching. I can have both of them simultaneously. And we have this for all edges. So for example, I'm going to write some of these out because I'm going to need them later. We have the node B here and has an edge to 1. And this can be that this edge is in the matching and also the edge that goes to 3. Similar, we can have the edge 1 and also the edge 5. That's over here. And then let's do one more, namely, oops, this one. B3 and B5 can also not be at the same time in the matching. Right, and you just like have these constraints for all of the variables, and now we have like encoded our matching. And now the idea is that we want to run like your favorite matching algorithms, maybe using some alternating path. Maybe you just do it greedily and choose your edges yourself. And then we want to prove that we have an optimal matching. But before we can do this, of course, we need to like talk about what rules we're going to have and what we can do. So first, we know that the variables are 0 or 1, so we can just add a constraint saying that the literal is at least 0. So for example, let's say let's have a column for the rule that we are using. Then we might need some annotation. And finally, we get as a result a new constraint, right? And then we want to use the literal rule. The annotation is the literal that we want to derive it for. Let's say we use it for x f6. That's like the edge corresponding to this. And we want to say that this variable is at least 0. So that's the new constraint that we now have added. Okay, that's maybe a super boring case. So let's do something more interesting. We can just take two constraints and add them. So we just add the left-hand side and the right-hand side, and then it's not too hard to see that whenever you have a solution that satisfies like both of these constraints, then it must also satisfy the resulting constraint, simply because like the left-hand side will add to the same value and the right-hand side will add accordingly. So again, as an example, we can use the addition rule on the constraints that I just wrote out here. So that was, let's say this is 1, 2, 3. So the proof needs to talk about which constraints it has. So it has some reference to them. And here on my slides, I'm just using these numbers, right? And let's say we want to add 1 and 2 together. And then we are just like getting the constraints. We have like xb1 appears in this constraint, but also in this. So we will have it twice. We will have xb3 once, and we will have xb5 once. And we added 2 constraints, so we get a 2 here. And now we can repeat this. And we can, like we have a new constraint now, right? Let's give it the number 4. And we can take the constraint 4 and we can add the constraint 3 to it. And then we have still the same literals, but now all of them appear twice, right? We have like xb3 once here and once here. So we now have all of them twice. Right, and this is like, it should be clear, this is like a super simple rule that's like very simple to verify. Like you just write a piece of code that does these additions and constructs this new constraint. And then we can also multiply constraints, that's fine. We can just like take any positive number and multiply the left-hand side and the right-hand side. And more interesting, we can divide constraints. And because we have integers only, we can round up, right? So for example, here, if you divide this constraint by 2, then all variables go from coefficient 2 to coefficient 1. The right-hand side goes from 3 to 1.5, but I know that the left-hand side must be integer because I only have 0, 1 variables. So I can round up the right-hand side from 1.5 to 2. And again, in our example, we can do this. We use the division rule. Then we have to say what we want to divide by. This constraint looks nice, so let's take it, 5, and we divide by 2. And the resulting constraint is actually a bit interesting because what it says is that at least 2 of these variables need to be false, which is the same thing as saying that at most 1 can be true. So in some sense, this is maybe even a better encoding that we should have chosen from the first point, right? Because that's what we want in a matching. We want that for each node, at most one of the edges that is adjacent to it can be in the matching. But of course, for sake of the example here, I use the clausal encoding just to show that it doesn't really matter how you encode it because we can use the proof format to translate from one encoding to the other. And this is actually important for some applications where different algorithms might prefer different encodings to make it easy for them to do proof logging. So it's really nice if you can do this translation from one encoding to the other. And of course, this should get a new number now. Okay, and so far, this proof system is known as cutting planes, which is studied a lot from improved complexity. But we are kind of the first that actually try to use it to produce certifying algorithms. Another rule that's used in solving is the saturation rule that we have, where the idea is if you have a constraint that has very large coefficients, so we only have positive coefficients here, so this constraint is satisfied as soon as we set x1 to false. And it kind of doesn't matter that the coefficient is much larger than the right-hand side, because as soon as we set this thing to false, the constraint will be satisfied. So we can also just use a smaller coefficient. So we have a rule for this also. And here we already start noticing that, oh, maybe it's not so few rules, right? Like, do we really need the saturation rule? And here we have to take a trade-off. Like, it's much easier to use a saturation rule. And we have even a paper studying theoretically that you can't easily replace it with a division rule. So here we already start seeing this trade-off between simplicity of the proof system, but also like ease of use for proof logging. All right, we need some more notation, so we can just negate a constraint. So if you want to say that at least 2 of the variables are true, that's constraint is falsified or negated if you say that at least 2 of the variables are false. We can use substitutions, which is replacing one variable by another. So for example, we can replace x by z and y by 1, and we can apply this to a constraint. And then we just you plug in the substitution, you simplify the constraint accordingly, and you get a new constraint. And then, by the way, a total assignment, if you want to define it formally, is just a substitution that sets all variables to 0 or 1. And then the constraint just evaluates to true. And we can also compose substitutions together. So if we have 2, we can first apply 1 to a constraint and then the other. And finally, we need the concept of implication. So we say that the formula implies a constraint C if every assignment that satisfies F also satisfies the constraint C. All right, so far, the rules that we have seen always are guaranteed to preserve solutions. So if you have a solution to the constraints that you use for these rules, then you also have a solution for the resulting constraints. But that's a bit stronger than what I promised earlier, namely because I said that actually we only need to maintain an optimal solution, right? We don't care about solutions that are not optimal. Feel free to add constraints that remove them. Because we're interested in proving optimality of the problem. So in our example here, we have, for example, the edge F6 here. And somehow I would like to say that, well, actually, I mean, come on, this variable needs to be true. Like it doesn't have any other edges. Like obviously this variable needs to be true, right? The problem is only that now again, like we have valid matchings that don't set these variables to true, but it's not an optimal one, right? So while it's obvious here in this example, and actually you can essentially just state it in the proof format also, and then the verifier will take care of verification. Of course, we want to understand like how this works, how the reasoning behind such a rule can look like. And that's what we're going to do now. So let's start with an initial idea. So we have this constraint C that we want to add, but we know that there's an assignment that falsifies this constraint, even though it satisfies the formula. So we like, it is a matching, but it doesn't set this one edge to true. Well, if we just find another assignment, that's better. That's just what I said, like, but actually just set this edge to true, right? Set it included in the matching. And then clearly the other solution isn't optimal, and we can replace it. So then it's okay to add C. So the idea is that we can add C if we find for all alphas that falsify this constraint, another assignment that's better than this. Okay, but now you should say like, but wait, didn't you promise us that this whole thing is efficiently verifiable? I mean, come on, like you can't enumerate all the possible assignments and then just give me a better one, right? So that's not a solution that nothing we can do. So instead of providing like the better assignment right away, I'm just going to give you like an instruction how to get a better solution. And we're going to do this by substitution. So in our example, we are going to just set this one variable to true. And then we're going to check this magic condition that I have here that I'm going to explain a bit more in detail shortly. But the idea is that if we have an assignment that satisfies the left-hand side, then just by definition of implication, it will also satisfy the right-hand side. And we can use this to construct this better assignment. So let's do this. So let's assume we have an assignment that satisfies the left-hand side. Then, as I said, by implication, it also satisfies the right-hand side. And now we just will use alpha prime to mean the composition of alpha and the witness that we have. And then it's just rearranging terms a bit. So we know that if we apply alpha to the right-hand side, this whole thing will evaluate to true. But it's just, we can just rewrite, right? We apply first omega to f and then alpha. That's the same thing as writing it as this, right? And here also we first apply omega, then alpha. Let's just be writing. And here we had f before, like the objective function, and now we just apply alpha to it. And then, as I said, well, just alpha prime is going to be the composition. So again, just rewriting. So we know that this thing on the top here is the same as the thing on the bottom, but we know that the thing on the top evaluates to true because alpha is guaranteed to satisfy this. But this also means that we have now an assignment alpha prime that satisfies the formula that's saying here, and also that we know has a smaller objective value than alpha. So if I manage to show you somehow, I didn't talk about yet how we're going to do that, but if I manage to convince you that this condition holds, then you should be happy because you know, in case you wanted, you could always construct a better solution. You're never going to do this during the verification step, but you could. So you know we can find a better solution. All right, so we have this condition, but then again, I only move the problem a bit forward because now we have this implication. And that's, again, hard to check in general. Like, how are we supposed to check that, right? But we want something that's efficiently machine verifiable. And well, the idea is just, well, provide a proof for it. We are just going to like decompose this like larger thing into smaller things and provide individual proofs, which are going to be, again, proofs of contradiction. How are we going to do this? Well, if every assignment satisfying the left has to satisfy the right, this means especially it has to satisfy every constraint on the right-hand side, which is the same as saying that if I negate that constraint, I don't find a solution that satisfies the left-hand side and falsifies the right-hand side. And now we just are left with the problem of unsatisfiability again, and we can use the proof format that I just presented you so far to like show show this implication. Right, so then this gives us a rule, right? Like we just have this condition that we want to check. If this condition holds, we can derive the constraint. And then the rule is annotated by the substitution that we're going to use, and then also by a proof for all these small steps. So in our example here, right, I wanted to derive this constraint, and we are going to use as witness just, well, if you have a matching that doesn't contain this edge, I mean, just set it to true. And then the next thing is, okay, but how would we need to annotate it? Sadly, I don't have the time to go into detail. But it turns out that, as we will see later, the verifier is taking care of a lot of simple cases. And for this, it will only be simple cases. So actually, we don't need to provide these proofs because it's so obvious that the verifier can just figure it out himself. All right, similarly, or not, I mean, related was actually, I presented like in reverse chronological order because like dominance rule is newer, but I think it's easier to explain from an optimization setting. It turns out that the SAT community had a very similar rule all along. And in our setting, it's easier to explain that so far, like the previous rule, we improved the objective function strictly, right? We made some sure that we get an assignment that's strictly better for every assignment that we removed. But again, like as long as we have one optimal solution, we should be happy. So let's allow removing optimal solutions as well as long as some solution is left. And then again, the question is how we're going to do that. Well, we use the same concept essentially as before, just that now we are going to say like, well, let's say you have a solution to all the constraints so far, including the formula. And this assignment also falsifies the constraint you want to add. So we want to add di. Then I'm going, with omega, give you an instruction how to modify this assignment so that you get a new assignment that satisfies everything we had before and the new thing. And I also guarantee that it's like not worse in the objective function. And again, the rules annotated using a substitution and with these proofs. So in our example here, look at this. Let me actually move this down. Like we have our small graph here, and then G only has like two edges connected to it that again are not connected to anything else. So I know one of them must be in the matching and the other can't be. So I can just say without loss of generality, let's just say that this constraint must be true. And what this is saying is that I can't have G7 in the matching, but not G8. Right, so I'm kind of, I don't like this matching, I no longer like. So I'm forcing to only have this matching now. Because of course I can't have like both matched. And then what's the witness for this? Well, I mean, whenever I get the matching I don't like, I'm just going to swap the variables. So whatever G7 was, G8 was before, now gets assigned to G7. And also the other variable gets swapped around. And again, this is so simple that the verifier will be able to figure it out himself. Yeah, sorry. All right, nice. Okay, so I kind of hand-wavingly argued why you should be happy with the rules I gave you. Let's talk a bit more in detail about it. So the idea is that we want that at least one optimal solution satisfies all the constraints that we added. And then if you think about it for a moment, it's not too hard to see that the following invariant is preserved by all the rules I presented to you. Namely that assume we have already an optimal assignment to the constraints so far. Then I will have potentially another assignment that satisfies also the new constraint that we added, and it will have the same objective function. Again, for the rules we had in the beginning, addition, division, and so on, you can just use the same assignment because no assignments get removed. For the dominance rule, well, we have an optimal assignment, so it can't falsify whatever we added, because then otherwise you would find something better, which would contradict that we had something optimal to begin with. And also for the last rule, I made sure that I can construct a new solution whenever I remove something. And this now proves that indeed, whatever we manage to derive, every optimal solution, or at least one optimal solution, has to satisfy. So let's go back to our proof. So I already discussed that we can derive like this constraint here for B, which is just saying that at most one of these variables can be true. So let's call this constraint actually at most one B. And then let me just copy this because I'm getting a bit short on time. Why isn't it working? I can just do the same, like just the same derivations, but for, let's say, D, for example, which also has these 3 edges, I can also do it for the node 4, which has 3, and the node 2, which has 3 edges. And we have like these constraints together. And now I want to just add them together. So I'm going to take like the at most one constraint from B, the one from D, 2, and 4. Let's see what happens. So this is going, right, it has at most one constraint. So if we take the one from B, we're going to have this variable, and this variable. If you're taking the one from D, we get these variables. If I take 4, I get these variables. And if I take the ones from 2, I take this. And now we should see that, oh, I actually have now all variables for all the edges. I also want a variable for this guy. So let's use the one we have here that I didn't give a number. So let's add this also. And I would like the variables for these guys, which is just one of the axioms we have. That's just saying not G, not X, G7, not X, G8, 1. I mean, I can derive this and get a reference for it, right? So now I have, on the left-hand side, I now have all of my variables, right? So I, J, the edges, and negated. Like I made sure like these are all negated variables. The at most one constraints have them all negated, and also this guy has negated. What do we get on the right-hand side? Well, for all of these at most constraints, I pick up a 2. So that is then an 8. From 3.5, we pick up 0, so still 8. And from here, we pick up a 1, so we have 9 now. Right, so I just derived this constraint using the rules in the proof format. And what is this constraint? Well, if you look again at the top at our objective function, it's a bound. Right, but this constraint says that at least 9 of these variables has to be true. And by the invariant I just showed you, we know that this means if you have an optimal solution, it must satisfy this constraint. So there can't be a better solution than 9.
You mean that is 9 and the variable has to be 4?
Yeah, false. So like these are like, we have like, in total, we have like 15 edges. So this is saying that we can have a maximum of 6 matched edges. And then we can like try to find the matching, right? Let's just like, I don't know, let's take some random edges, maybe these. How many edges are these? 1, 2, 3, 4, 5, 6. So now we already know that 6 is the optimal number, right? Which you can't, if I just mark them, you don't see that obviously. Like it seems like, oh, here's a node left, here's a node left. Can we find something better? Well, no, I just showed to you that every matching has, this has the best value possible. All right. Perfect. We have that check mark. Let's move on. So one thing that a lot of algorithms do is that they don't do this. I mean, what I showed you now is a bit ad hoc, right? I just gave you the proof. I gave you the solution. Now you're happy. A lot of optimization algorithm in combinatorial optimization work by incrementally finding a solution and then saying, well, now I want a better solution than that. And once we can no longer find a better solution, we know we're done. And like we also have a rule for that just says like, well, whenever you satisfy the formula, you can just add a constraint that says you're looking for something strictly better. And then this rule was annotated by the solution that you're using. So we can use the bound rule. And then we use the matching that I just marked as a solution, like in the proof file, it's annotated by the solution. And then we had a matching of size 6. So I want the constraint that says I have a better matching than that, that's saying, well, at least 7. And what I can do now, where did I left? I guess 6 and 7. I can now just take these two constraints and add them together. Like the lower bound I have that we derived using the rules, and the upper bound we have that we derived using the solution. And what we will get is just a contradiction, right? Because we can't have such a good solution because we just proved the bound for it. And this is kind of nice because this means that now we can actually end all proofs with contradiction. Not just the ones where we don't have solutions, but we can, like, it's kind of more standardized in a sense. All right. Okay. We also have a rule for deletion that's mostly for performance reasons. For example, if you derive a lot of constraints, at some point you might run out of memory, so you might want to delete some of them again. Can also have a performance impact for the automatic proving that I will talk about shortly. And in theory, it seems like, well, I mean, if you delete constraints, it makes it only more satisfiable, right? Like what can possibly go wrong deleting constraints? Except it turns out things can go wrong if you don't do it careful. It's not too terrible. Something I can talk about in the second half in combination with dominance, it suddenly becomes a bit important how you do deletion and when you do it.
Stephan, you got a question about the bound rule or the model improving
yes.
Rule that you maybe should explain. The question was, does this mean that it takes linear time to, because you need to verify that the bound satisfies all constraints? Does this take linear time?
Yes. Yes.
But this is not the function of the bound constraints, right? You're not verifying it, you're using it to drive
No, you verify that it actually satisfies the constraints.
When you log the solution.
Yeah, like you like the bound rule, like you log a solution with the bound rule, and for this rule to work, you want that this actually is a solution, because otherwise you did a mistake, right? And we want to terminate as early as possible. So we will actually check that the solution satisfies the constraint.
The one thing that the bound rule will do, it will actually insert, you give it a solution, you insert it.
You can optimize this a bit using propagation, but essentially you will check the full formula if it satisfies is satisfied by this assignment, which in the worst case is linear time. But like it's not really a problem, because usually the number of solutions isn't that high, so it's rather a rare occurrence, and then it doesn't matter too much if we spend a bit of time on it. All right, I should speed up a bit. So one problem is that programmers tend to be lazy, and we want it to be easy to be verifiable. So we want just the obvious things shouldn't be taken care manually. The verifier should take care of obvious things. So what is an obvious thing? So for example, I talked about this condition for the dominance rule that we have, and then you just don't need to give a proof if, for example, one of the constraints is already a contradiction, right? Obviously, like, I mean, this can figure it out itself. Or maybe if the constraint we want to show is implied is already in the formula, then it's also no reason to like give a manual instruction for this. And there's like some cases that are just like covered automatically. And you can also do something slightly more intelligent, which is reverse unit propagation, which has been very successfully in stat solving. So assume we have like these constraints as shown here, and we want to add C3. And then of course you could just start adding things, maybe do some division or so to derive it. But we can also just claim that there is no solution that satisfies C1, C2, but falsifies C3. And it's actually in this case, not always, but in this case, it's easy to check using unit propagation, which is just setting first variables. So C3 is only false if both X and Z are 0, right? But if X and Z are 0, then C1 is only satisfied if Y is set to 1. But at this point, C2 is not satisfied by rho. And this means there's no assignment that satisfies like C1, C2, and falsifies C3. So then it's fine to add C3. And like there's like a very efficient algorithm for like figuring out which constraints force some value, which are like developed from the solving side, but can also be used here on the solving side. All right, we're getting towards the end. What is left to be done? Well, performance of our verifier can still be improved, I think. One way of doing this would be to try out doing a binary format. Right now, we have like just a text format that I can show in the second half. And then you could also, instead of binary format, it could also be interesting to try on-the-fly compression, especially because most of these tools don't make that much use of parallel computation, but most CPUs nowadays have multiple cores, so you could just use one core for compressing the proof to have like less stress on the disk for writing it out. Then also something very amazing that DRED is able to do, DRED trim, and which is a tool for verifying DRED, is to like trim the proof while it's checking it. So instead of like going from the start of the proof and going towards the end and checking every step, it's starting from the back and then only checks the steps that were actually used. Because it happens that solvers do a lot of reasoning, but then later on realize it was the wrong direction they headed off and don't use it anymore. So that can also improve performance, of course.
Maybe you're getting there. Yeah, I guess we're getting there now. There's a question in the chat whether VeriTV itself is formally verified.
Yes, so that's already the next point. And no, sadly not yet. We started working on it. And there doesn't seem to be like any fundamental challenges in doing so. It's just that the process takes some time, and also like getting these formal verification tools to have nice performance and so on. It just takes some time, and we kind of spend more time on trying to figure out what we can do with this proof system and how it should look like in its full beauty. And then later, like now, we want to make sure that we also have a tool that is able to formally verify it. So right now, it's just written in Python and C++. So it's not unlikely that the verifier has errors. However, even if it has errors, I think you should trust it more than not using it, because again, it's like giving your work to a colleague and letting a colleague check it, right? First, its colleague might also like not realize things, but just by you expressing your reasoning and letting somebody else looking over it, it's quite likely that you find a lot of errors.
But if the answer is, Stephan, that we should stay tuned and wait for a formally verified version of VeriPB appearing soon in a conference near you?
Yeah, I hope so.
Okay. And another question, can you integrate your tool into a more general CSP solver?
Yeah, like, so we have some of our work we have is doing constraint programming. I think CSP refers to constraint satisfaction programming. And there, the problem is, first, of course, you have to like describe what these different constraints that you have mean in a pseudo-Boolean setting, and then you have to express the reasoning of the different algorithms. And the challenge there is that there are a lot of different algorithms. Some are very easy to do proof logging for. Others might be more challenging and require some thinking. But like, for example, like we have seen matching in our example, and like the different propagator is based on matching essentially. So we can like use that thing to like verify the propagator.
And you might want to advertise an upcoming paper on this topic, which one of your co-authors is suggesting in the chat.
I didn't have the chat.
Like a CP22 paper on constraint programming.
Yes, like this is an audible constraint programming solver, and it's on the. I don't know if I find it quickly. Where do I have it? That's this one, GMN22.
So yes, there is work on proof logging for constraint programming solvers,
yes,
using this method that we have followed.
So we can do a lot of things in constraint programming already. But I think there's also room for future work to like do even more of the things that are possible there. But I think we are on a good road towards it. Yeah, which is kind of the last point also. So kind of the questions getting ahead of my slide right now. So we want proof logging for more algorithms and problems. So like at the beginning, we had a list of things we can already do. You can also use this for maxat solving. I think this proof format will also be very useful. We can do more propagators than we already have in constraint programming. Symmetric explanation learning is something we cannot do yet, and it might be possible, but I think we are not completely sure about that yet. And also, one could try using it for some things in integer programming, or maybe use some of these techniques and generalize them from 0-1 variables to integer variables, and then use them in integer programming. So in conclusion, proof logging is very well established for SAT solving. But so far has not been usable for some techniques in SAT, and also for richer problem formalisms. And our work is proof logging via pseudo-Boolean proofs, and then the verification with VeriPB. So it's like always two sides, right? You need to like design the algorithm so to produce a proof, and then we need the tool that checks the proof. And I believe that it's reasonably simple to implement these proofs and also to check them. And it's applicable to a wide range of, especially combinatorial algorithms. Like, as I said, pseudo-Boolean solving optimization is like an NP or NP optimization problem. So anything you can reduce to that is kind of lends itself to also try using our proof logging for. But also, I think one could even imagine using it for simpler problems in P, as long as it's easy to describe what the problem is in pseudo-Boolean. But like the algorithm is somewhat involved, you can then try to express it using these reasoning steps, like we have seen here for matching, to then have like a certifying algorithm. And we have managed to like resolve some of the open problems for proof logging for SAT all-value business. So I think it really is a very promising approach to certifying algorithms. So thank you for your attention.
Okay, thank you, Stephan. So I'll stand here so that I'm visible. If there are any more questions from the physical audience or from the chat, then please ask. Otherwise, we'll take.
Stephan.
Yes.
Stephan, thank you very much. A very short question. I don't know whether I missed it, but I assume that implicitly new variables are allowed as well, correct?
Oh, yeah, I totally didn't talk about that. Yes, yeah, you can. It's kind of important for some things that you're allowed to also introduce new variables.
Yeah.
With the proof format, and you can do this with the redundance rule. Because I mean, you can also think of, I mean, what is a new variable? New variable is a variable that doesn't appear in the formula, right?
Yeah, yeah.
Oh, you add a constraint with this variable that wasn't there before, but you could also pretend that the variable has been there all along. It just didn't have a constraint with it, right? And then it's just saying like, oh, I want to add a constraint that is restricting this variable that wasn't restricted before.
I see.
How I remap the solution that contains this.
So at least your system, proof systems, as strong as extended free.
Yeah.
Okay, cool.
So yeah, that's an interesting aspect. So extended Frege is kind of one, if not the strongest proof system that people know. And then it's kind of nice if the proof system you have is able to like simulate this, which means you could in principle translate proofs. But one problem is that just the ability to do that doesn't mean you can do it efficiently. Just like, for example, we know in theory, DRED should totally be able to do all the things with proof-built constraints that we can also do. The only problem is like, can I really do it efficiently, especially if the coefficients get very large? And then it can just be that the overhead is too large.
Yeah, I think that makes your system very interesting.
Thank you.
Any other questions?
I have a question. So for matching, at matching, we also have potential that if there's no augmenting path, then there's no larger matching, right? So would the derivation rules that we talked about, would they potentially also then result in such a proof, basically?
Yeah. So you can read this in my thesis, actually, because I have this example in my thesis. So the way I usually do maximum matching is that you do this augmenting path algorithms, and at some point you are at a state where you can no longer find a better augmenting path. And then once you reach this state, it's very easy to read off which nodes have been reachable via an augmenting path. And then there is a result from graph theory known as Koenig's theorem that states that you get was it vertex or edge cover? I never can take these two apart. Like the one where you have a cover of all the edges, and it has exactly that property, namely that it has like the size of the best matching. So you essentially, after doing the matching algorithm, you read off just what constraints you want to add. Like it's very easy to then see immediately, oh, I want to add most one constraint for these nodes. Just add them together, you have your load on.
So, Stefan, how long a break do you want to take before the second part?
I don't know, like 5 minutes, 10 minutes. I think we also, in the physical room, we have some fruits.
Yes, so now everybody in the physical meeting now will go and have snacks and coffee, and it looks really delicious. And the virtual participants waiting for the second half, you'll have to go get something on your own. We'll reconvene in 10 minutes. And thanks to everyone who joined the first half and who are leaving now. Let's conclude by thanking Stefan again. And so we're back after the break, and Stefan will now continue with the more the technical hardcore part, where we will actually see the innards and see very PB in action, accepting and rejecting maybe even proofs. Please, Stefan, the floor is yours again.
Yeah, so like, I mean, it kind of depends also what the people or the audience would like to see. So I can try to do a live demo of the proof format and the verifier. We could talk a bit about how to translate from direct proofs to our proof format. The versions of the dominance and redundance rule were a bit simplified. We could talk about default rules. I could also talk a bit more about like comparing the dominance and the redundance rule. And we could look at a tiny example of why a deletion can go wrong with the dominance rule. I don't know, can I actually make votes?
Do you want me to do a poll where people can vote?
If you can do a poll.
And you have to read the alternatives. I see if I can do a poll. Let's see.
Otherwise, I just do something. Or if there are any questions.
What's the first live demo? Is one?
Yes, live demo. Translating direct proofs.
Translating direct. Next one.
More on dominance and redundance.
Fourth one.
Deletion and dominance.
Those are the 4 options we have. This restaurant has 4 courses on the menu, or 4 menus. So more on deletion and now it's extremely exciting. Because now there's a poll. Let's see if we can make the poll live.
It's the audience also want to vote.
And I'm launching the poll now. And I don't know if you can answer only for your favorite alternative now. I'm not sure. Is it single choice? Okay, I guess maybe if I had configured more carefully. Oh, single choice. Actually, I'm making it multiple choice now. What happens now?
So like hand signal, who wants to see live demo?
It should be multiple choice now.
Who wants translating direct?
Yes, it's single choice.
More on dominance and redundance.
So I think we're seeing more for translating.
Yeah, I guess we're just going.
Dominance and redundance. I would like to vote a little bit for live demo, but maybe you will do that for dominance first then.
Yeah.
Direct seems to be the most popular thing.
You can also try not to take too long.
Yeah. So is it direct first, then more on
yes.
redundance, and then it's possibly a demo?
All right. So what is direct even? So essentially, you can think of direct as just having the redundance rule and only having clauses. And also, like in the redundance rule, we had this witness that we used. Like here, we applied the redundance rule and we like substituted variables with others. And this witness in DRED is just implicitly defined as setting the first literal on the clause to true.
For people who don't read dynamics, can you write down what that first clause is?
And the way clauses are stored is just that we have only numbers. So like x1 is represented as 1, x2 as 2. -3 means not x3. And then everything terminates with a 0, like every clause terminates with a 0. And then the way to translate this is essentially to like just rewrite that clause into the Boolean form, which is happening here. So you have to give a coefficient because we can also have like more than one as a coefficient. Then the variable, which is x1, because we had a 1 here. Then we have a 2, so that's x2. And then negation of a variable is not done with a minus in the pseudo-Boolean format, but with a tilde in front of the variable. And then it's a clause, so it's greater or equal to 1. So like this, what is marked here now is just exactly the same as that's written here, just in like not Dimex format, but in pseudo-Boolean format. And then for our format, you have to explicitly specify what the witness is. So we want to set the first variable in the clause to true. So that's x1 and just setting it to true. And then the way our proof format works is that we have like these different rules, and like each rule has a name that you use it by, and the redundance rule is just red. Then the constraint you want to add, and then the witness. So to translate this DRED rule is like really extremely syntactic thing. Like just take the clause you want to add, and instead of like outputting like this clause thing, you output like this more verbose text thing. Which also, I mean, immediately clear that if you are in a text format, it will be a bit larger. And then one difference is also that in the DRED proof, like the formula is kind of loaded implicitly, like you already have the constraints from the formula. While in the pseudo-Boolean proof, you will first need to load the formula manually. But then after that, it's just like translating step by step, like these DRED steps. And the reason this works is really because the redundance rule was designed as a generalization of DRED.
Just a question to get this crystal clear. So what you're saying is that for people who know how to use DRED proofs, lines, every line will be something like the above, positive and negative integer, terminated by a 0. And just syntactically, whenever I see a number on that line, if I want to turn it to your proofs, I just add a 1 in front for the coefficient, and then instead of 42, I write x42. And then at the very end, I write greater or equal 1 semicolon.
Yeah, exactly.
And then if the solver knows that it is the rat rule, then I write, oh, very first literal maps to 1. And that's like the correct syntactic translation from the rat to very easy. Is that correct?
Yes.
So what is this witness thing or witness method?
I mean, this witness thing is like, where did we have it? I guess the rule, right? And that's the witness is what you use for checking the rule.
Is an axiom, right?
The witness is given as part of the proof.
So what I confused about is that, so now we are adding an axiom from that.
No, this is like deriving a new constraint. Oh, sorry, yeah. So the axioms from the formula, like the constraints from the formula, you don't need to say anything about them in the DRED proof, and you're just like dumping the clauses you want to add. And DRED does not allow you to give a proof for why this condition that I showed you holds. So it needs to hold by unit propagation so that it can then check it automatically. Sorry? For the witness? Like it's specified that DRED will always pick the first. And like the way this works for SAT-solver then is that when doing clause learning, it's just dumping the clause that learns, because it turns out you can always verify them by RUP even without using a witness. And then this check will still automatically pass. One small problem, as one that didn't show here, is deletion. So DRED can also delete constraints where you just say D and then again the clause in clausal form, in Dmax form. In our format, you have to write the del, like deletion, and then you can either delete by reference, which means you have to write ID and then the number of the constraint you want to delete, or you can also let it look up, try to find the constraint, which I think currently is del find, and then the constraint again in OPP format. It's like again like one-to-one correspondence. One small problem is that most SAT solvers don't report learned unit clauses. So it could be that, let me make an example on this whiteboard.
Connecting to Mark's question, do you also want to do a super quick, like, rapid, I don't know, sorry, I mean, like, just put this witness in what,
I would put this towards the dominance section, maybe. So let's say our formula is this x is greater than 1, and we know that x plus y is greater than equal 1. If we have this in our formula, then it's clear that x needs to be 1 and also y needs to be 1. And the thing that most SAT solvers do now is that they like store these unit clauses, but they don't emit them to the proof. But now these constraints are satisfied, so they just delete them. So now kind of the SAT solver deletes these, especially this constraint gets deleted. But the SAT solver didn't report that it learned y is greater than equal 1. So that's actually then the VeryPP will fail in this case, because if you delete this constraint, then well, y no longer know that y is greater than equal 1. But the way that DRED trim works, which I think is more of a historic artifact, also it's nice when coding up these propagation things, is that also DRED trim kind of stores these unit propagation separately, so that DRED trim, if you delete this constraint, it will still know that y is greater than equal 1. So like then SAT solvers don't report it, they delete the constraint, which is kind of a small difference in the behavior of the verifiers. So if you want to use VeryPP for SAT solver, make sure that you report on the unit clauses also that you're learning.
To be clear, this is a violation actually of the DRED format, but it's just that solvers and verifiers sort of have agreed that they accept proofs that are buggy in the sense, and that's what it works.
Okay, then I guess let's talk a bit more about dominance and redundance. So I could actually maybe let me make this example first a bit more explicit with the witness and what we have to do. And I think the more interesting one is like this step here. So let me just grab this. And let's have a look at this slide. That's the rule we have. So this guy here is the constraint we want to add, right? So that's di. Or like, I guess I'm not sure the, yeah, let's just call it di. And we can use all things that we have derived before. We can use the negation of di. So what's the negation of this guy? So we have that's the constraint. To negate it, essentially all we want to do is say like, well, it shouldn't be greater equal, it should be less than. Now let's again rearrange it to have only greater equal constraints because this makes it much easier to work with. So first we are flipping the sign of the comparator to make it greater, which is like putting a minus, like just multiply by -1, everything is the same as like to flip the sign. Then we know we are Boolean. So if we are greater than -1, that's the same thing as saying we are greater equal as -1 plus 1. Did I do it right? Yeah, so before this was strictly larger. Now we increase this by 1. So now we can be equal or larger. So that's the 0. And then we want to get rid of the minuses also. Well, this over here is just saying -1 minus xg7. And then we can also think of having a 1 here if we add a 1 here. So we have -g8. As I just add a 1 on both sides of the inequality, which is not changing the inequality. So now we have like -1 here still left, minus disappears. So we have now the positive variable. Then this guy is again just a negated literal. And I have greater 1. So then let me move over this -1 to the right-hand side by adding 1 to both. That gives this constraint. This keep is very annoying. So that's just a negation now. That's like not di. And I don't need these guys anymore. So we can use this guy and we can use the formula we have. And here you can already see like this forces these two variables, right? And then the witness that we have is swapping G7 and G8. And then we have to look at, okay, what does this do if we apply it to the constraints we have derived so far and the formula? So in the formula, we have one constraint that is affected. So from formula, we have the constraint that is like containing these two variables, right? Saying that not both can be true. So we have G7 x G8. So if we now take F and apply omega to it, what we get is, okay, actually it's the same constraint, right? Because we're just swapping things. Like we're swapping 7 and 8 and 8 and 7. So if I swap 7 to 8 and then 8 to 7, I get the same constraint I already have. So we have these guys. And need to show okay, so this showing this guy is easy because like I mean, we already have it in the formula. So clearly it's implied. Then we need to show that di restricted by omega is also implied. What is di? Oops. Restricted by omega. Well, again, we're just swapping 7 and 8. That's di. So we have xg8 because we replaced g7 by g8. And we have xg7. Again, because the substitution says that we replace them. Okay, but we know already that xg7 is true and xg8 is false. So it should be clear that whenever we have an assignment that satisfies not di, then this guy is also satisfied. Yeah, actually it's even stronger, right? Like, I mean, actually it's kind of the same constraint, except here we have a 2 and here we have a 1. So you could also just reduce the coefficient here to derive it directly. So this guy we have, and then we have to show this. Okay, the objective function is a bit long, right? Because it contains a lot of variables. But again, like almost none of the variables is touched by omega. And the ones we do touch, we just swap them. So actually, we still have the same variables on both sides. So then this constraint is actually trivial because it says that something is less equal than like the same thing. So, well, that's also fine. So as I said, as I promised, like for this example, all these implications are kind of obvious and the verifier can just figure out himself how to prove them, but you could also like manually do it. Maybe this makes it more clear now what this witness is used for and how it works. Mark, or no? Okay. And like the nice thing is really like, I mean, on the one hand, look, we have this rule, right? And like at some point we convinced ourselves that it works. We probably forgot already why it works, but we can just like mechanically check it, right? And like, if you need to know why it works again, because maybe we want to use a formally verified solver, then we have to unpack this and like think about why this works. Oh yeah, it works because omega gives us an instruction how to remap assignments. In case we have an assignment that falsifies the constraint we added, we can construct a new assignment that satisfies the constraints. That's why it's fine to add it. But it's like the reason why this rule works is kind of not what we check when checking the rule. Right? Checking the rule is way simpler. We just mechanically check the conditions. Are you monitoring the chat, Jakob? Should I try to do it?
Yes, I am. Yes, it's here.
Right. So then something I wanted to mention in the talk, or I'm clear if I should have mentioned it, but that I find interesting is when we compare. How do I get rid of this bar? Like somehow the dominance and redundance rule are somewhat similar, right? We have this witness that gives us an instruction of how to get the better assignment. The main difference between these two rules is that the redundance rule is really like, oh, you had a satisfying assignment before. Now here is a satisfying assignment after adding that constraint. So like it's extremely explicit in that it's like directly giving you the, if you have an assignment satisfying all the constraints before, you can directly construct an assignment satisfying all the constraints after adding it. The dominance rule, on the other hand, is slightly different because actually it doesn't guarantee you to give you a satisfying assignment. It just guarantees you to give you an assignment that's strictly better and still satisfies F. If you would want to get actually a satisfying assignment, like let's say you have an assignment satisfying F but falsifying C, like you can apply the witness to get an assignment that satisfies F and that is strictly better. But it could still falsify C. But well, then you can just reiterate, like apply the substitution again. You get a new assignment. Maybe you're still falsifying not C, like do it again, right? And then the thing is that we are over Boolean variables. We are only having a finite number of assignments and we are strictly improving in every step. So eventually this will terminate. It cannot possibly go on forever. But in some sense, this allows us to do a kind of inductive argument, right? Instead of saying like, oh, here you can add this constraint because here is how you get a better assignment. We say like, oh, here's this constraint. And if you really wanted, you could spend a lot of time of finding an assignment that is better, that is like satisfying the constraint. Like it could potentially require you an exponential number of steps doing this reduction. And it's kind of like an inductive argument saying like, no, actually, look, like if you have a case where we can inductively improve it and eventually you will get somewhere that is nice. And that is crucial for symmetry breaking because that allows us in symmetry breaking to do it like efficiently and break every symmetry only once. Because it turns out as like it works like similar to this, like you add a constraint that removes your symmetry and you say like, oh, how do I fix my assignment now if I have one that's blocked off? But if you have multiple symmetries, it could be that they like influence each other. So maybe you fix one symmetry and now you break the other again. But then by this inductive argument, you can just like, you know that it will eventually work out and you will have eventually left something that satisfies all your breaking constraints. It's like really powerful inductive rule that we have. All right, and then these are the simplified versions. Like in the actual proof format, we are allowing more flexibility. So the dominance rule, as I presented it, requires you to improve the objective value. But what if you're in a satisfiability problem? Like you only want to know SAT and unsat, your objective function is just 0. Well, you could just come up with your own objective, kind of. Like you can define your own pre-order on assignments, and then the dominance rule will strictly improve in that pre-order. And the way to define this is by giving a set of constraints in a certain way that defines a pre-order. So we have like two sets of variables, U and V. And if you plug in your solution, like one assignment to U and the other assignment to V, you compare the two assignments. And then these pseudo-Boolean constraints should be true if indeed the assignments are less equal, and it should be false otherwise. And then we have like a set of constraints since the last time the pre-order was changed. So you can say like, oh, first let's go in that direction. Let's use this order. And then you can switch and say like, no, now I want this order. But you kind of have to then remember like all the constraints you have derived at that point, like at the point where you change it. So if you have just the objective function, then this is always just the formula. And you can also then have you also have the set of constraints that you derived in the meantime. right? Maybe we used the dominance rule already 5 times since we changed the order, and then all these constraints will end up in D, while the formula is still in C. And then you can, if you like, push the conditions a bit, like the more stuff we get on the left-hand side, the easier it becomes to prove things, right? Because then the more we can use. And it turns out you can actually not just use the formula or the constraints you have, but you can also use all the derived constraints. And it doesn't break anything. And then it's just the same, essentially. It's saying that, well, if you have an assignment satisfying everything before, then we can construct a new assignment that is satisfying the constraints in C, which we call the core constraints. And the order is not getting worse. And we don't mess up the objective function. But now we only have kind of an assignment that is like better, but not strictly better. And to get one that's strictly better, we have this additional condition that says like, well, it shouldn't be the case. Like there's no assignment for which the order says that we are less equal. It's kind of saying not less equal by saying like, this is kind of a pseudo-Boolean language way of saying the order should improve strictly. And then you would, for example, if you want to do symmetry breaking, the order would depend on the breaking you want to do. And then also the redundance rule is similarly using like these more general concept, like they can have all the constraints that we derived before. Then we have the negation of the constraint we want to add. And we are going to get a new assignment that satisfies everything. And we don't mess up the order, and we don't mess up the objective function. And again, the key difference somehow is in this part here, where the redundance rule is saying like, yep, you're going to satisfy everything now. While dominance rule is just saying like, well, you're going to satisfy the core constraints. You might totally falsify the rest. But it's fine because of the inductive argument that we can. And this kind of gives the dominance rule its power. And the cost is then that we have the strict improvement, right? Like the redundance rule has only less equal, while dominance rule has this additional condition down here to guarantee that we have this strictly less equal. All right.
You're getting your question whether you can publish the slides somewhere.
Yes, definitely.
If you could push, I mean, you can put them on your webpage. You could probably also post them next to the video on the seminar webpage.
Yeah.
We should wrap up really soon. Could you make a super quick demo? Or
yeah. So that's again this matching problem that we looked at throughout the talk. Get this sample set. Doesn't like me. Yeah, so that's the matching problem that we looked at, right? We have like minimize, and here I just skipped the X. I just named the variables left node, right node. So we have minimize the negation of all these. And then I already have the at most one constraints in the formula now. So this constraint here is saying that at most one of the edges adjacent to D can be true. So this is actually, it's just the upper part. So this formula is just like this part up here. And then we had like D has an edge to 1, 3, and 5. So we have 1, 3, and 5 here. That's the formula. And then the proof is just saying load the formula, then add all of these at most 1 constraints together. So that's what we did. Which one is the one I had? Here, right? We added all of the at most 1 constraints together. That's happening here. This is using reverse Polish notation. So we have first the reference of the constraint, which is put on the stack. Then the next reference is put on the stack. Then I take the 2 topmost elements, pop them from the stack, add them. Then I push the next element on the stack. I take the top 2 elements, pop them, add them. Then we have the solution and adding a bound. And then we add the last 2 constraints together and we derive contradiction. And then to verify this, we use VeryPB. We want to see a trace to see what's going on. We want to use color because then it's easier to understand, to read. And then we just give it the OPB file and the proof file. I write my own tool name. Why is it not working? And then it looks something like this. What's going on? Well, it says like, oh, begin the trace. Your first command was to load the formula. So here is your formula. The first constraint is the following. The second constraint is the following, and so on. So now we have the IDs 1 to 10 in our database, and we can use them. Then the next line says, take 1 and 4 and edit. So like this guy, then 7 and 9. And then the resulting constraint is this. Right? It's just like the sum of these. Then again, like we have the objective function.
And you automatically give that a new reference then.
Yeah, so this now gets number 11. Then we can add a bound from a solution, which gives us a new number 12. And then we are just adding the last 2 constraints, 1 and 12 together. Which actually fails. So I messed something up, it seems. But I, of course, wanted to show you what happens if the verification fails, right? So somehow I probably have edited the file so that now the things don't quite work out. And then like we want to add 11 and 12. And what was supposed to happen now is that we get contradiction, right? But it turns out we don't get contradiction. That isn't a contradicting constraint. But then we claim that we have contradiction. And then, of course, VeryPB is like, what are you talking about? Like, no, it's wrong. So let's see if we can somehow quickly debug this. So yeah, so here, these guys appear twice. I only want them to appear once. Now the question is, where do they come from? E2 and E4, 1, 4, 7, 9. That is odd. I guess I should have tried this beforehand. Oh, wait, don't take. I wanted to add these guys. I want 4, 5, 7, 9. I don't take 4, 5, 7, 9. I have 1 instead. So let's fix it. I want to say 4, 5, 7, 9. And let's try again. And voila. Now it works. And now VeriPP is also happy, and like we get what we want. Yeah. Any more questions? Otherwise, I guess we can conclude. I guess Jakob's laptop is running out of the battery, which maybe is a sign. You should get to an end. Any questions? Things you want to see?
What would how detailed is the tracing if I'm doing one of these dominance or redundancy?
Not very. It just says you that it works or it doesn't if you use the automatic proving. If you give proofs yourself, then I mean it will, of course, report on the individual steps you provided. Let's see. So like VeriPP comes with all of test cases. So like a very easy way to see how things work is just look in the test cases. For example, here we have a test case that doesn't have a formula, it's an empty formula. The proof still loads the formula. Okay, that's probably not going to do much. And then we have a redundant step that is adding a new constraint. And like this is introducing a new variable because the formula is empty, right? And then essentially what this is doing, it's a clausal encoding of an end. So it's kind of saying let x1 be true if and only if let's see, I think like this, if I didn't mess up. And this allows you to add new constraints. And then if you feed this to VeriPP.
The line 6 with the x3.
Yeah, you're right. Yeah, that works. And the trace. Oh, because actually it's telling a bit more. I forgot about that. So what's going on is that it's kind of listing the proof goals that we have. Like we don't need to show anything from the formula because the formula was empty. We need to satisfy the constraint added. So like we have to show that this guy is implied. Which is obviously the case because I mean this constraint is trivial now, it's satisfied. And we have to show that we don't mess up the objective. Well, we don't have an objective, so that's also fine. And then VeriPP says, oh, well, yeah, actually, I managed to automatically prove the first proof goal. The constraint is trivial. And then it adds the constraint. It says like, oh, no, the first constraint you have is like this guy.
What it means by trivial, it means that the witness omega satisfies it.
Yeah, like after substituting the constraint with the witness, I have a constraint that has greater or equal 0. It's like a constraint that's always satisfied. And then like for the next thing now, we have another proof call, right? Because we just added this constraint, and the redundance rule is requiring that like you don't mess up the things that you added. So we get a proof call from that. And then again, we have to satisfy the constraint, which is again a trivial constraint. And then it's saying that one was trivial. It doesn't say how it proved the constraint from the formula. So definitely one could improve RAPP here, but also like giving more information on what's going on. But it's like it's managing to automatically prove it. And the way it does it is it follows directly from the negation of the constraint that you want to add. Which should be clear when staring long enough at it. And then maybe also like a small example of subproof. Like some of the test cases are also annotated with comments so that you can see what's going on. So here we again have a redundant step that is adding the clause x1 greater equal 1, and is like doing a lot of variable swapping around. And then again, RAPP will report like what things do you have to prove, right? So you can just read off the things you have to prove on the trace, and then you say like, oh, let me actually manually produce a proof for that goal. And this. So where comes the redundant step? Here, that's the redundant step. Saying we have the following proof goals. And then if you like have subproof, then of course, according to the rule, if I show it again, try to find it quickly. Right, we are allowed to use the negation of the constraint we want to add. So the very first thing RAPP does after giving you the, like we say we want to use redundancy rule, it's telling you what things you have to prove, and then it's providing you with the negation of the constraint you want to add. So we want to add x1 is true, the negation of this is x1 is false. And then you can say like, well, I want to prove proof goal number 1. So what was proof goal number 1? We have to show that this is true, that this is implied. How do we show that it's implied? Well, we show that if we have the negation, we can prove contradiction. So RAPP gives us immediately the negation of that constraint. And now we can do whatever, like we do some additions and stuff. And then ultimately we say like, oh, actually, now we have proven contradiction for this proof goal. So now we know it's implied. So this is like this. Right, we have like, for each thing that we have to show, we have a proof that I have the formula, I have the negation of the thing I want to add, I have the negation of the thing I want to show, and I prove contradiction. And that's like exactly what's going on here, like in this subproof. And then you do this for all the goals, and then you have shown that indeed you can add this constraint. Any other questions?
Stephan, there's one point, maybe it's a little bit off topic. You mentioned and wonderfully described this induction principle. I assume it is only finite. Is it correct?
Yes, because we have like a
otherwise
finite.
we would have a stronger system than extended Frege. Like then it would go into the direction to pay or something like that. So
yeah. No, but like because like we are only having Boolean variables, so the solution space is finite. So this is like everything is still finite. And
I just wanted to reassure that. Okay, thank you. Very nice.
Thank you, Stephan. And moving camera again, maybe. So thanks, Stephan. Thanks, everybody, for joining. And you're welcome again on June 10th, I guess, for Stephan's thesis defense. But then Stephan is not presenting. Then his opponent is presenting, and Stephan will be busy defending himself. So, well, anyway, thanks for today.